Well, good morning, and thank you to those of you that are here on time. First, actually, I have a question for you. I've been every week sending the Zoom code in the WeChat group, and I would like to know if you want me to continue to do that, or are you okay? So if you actually open the participants window, at the bottom you can see these two buttons that say yes and no. So if you want to just let me know, yes, please send the Zoom code every week, or no, we don't need it every week. It will just kind of help me know whether to do that. Or you can send a chat, but you can also just vote in the participant windows. Okay, so, well, 3 of you have said yes, so that's actually enough. Okay. All right, so I will continue to do that. First, let's go over the homework from this last week. Most of you actually did a pretty good job at it, and so hopefully you did it and didn't just copy it from before. But just again to review, if you see on your homework, if there's no comments, if there's no marks, that means everything's correct. So if you think I didn't look at it, you're wrong. I look at every paper, but if there's nothing there, that means you did it correct. As I explained last week, sometimes if I write work, that means you're not showing me your equations or your numbers, so I can't follow what you did. Remember, you must always show me both. Math means you have a math mistake. Question marks means I can't read it or I have no idea what you did. I asked a lot of you to please circle your final answers. I know a lot of you don't have that habit, but a lot of you, your papers are messy. There's a lot of information there that you don't even really need. So it just helps me if you put a box around your final answer. If I write units, your units are wrong or missing. This one I write a lot, SF, SF, SF. So remember we talked about significant figures. So you need to pay attention to those. And then you need to have your name and student number on every picture. And you should know that if you do not do any of these things on a quiz or an exam, you will lose points. So pay attention to these details. All right, let's go through the answers then. So the first one, number 9, they gave you some information, asked you to calculate absorbance, which is just minus log T. Almost everyone did this one correctly. Then B asked you to calculate the molar absorptivity. So remember, that's this symbol. If they just say absorptivity, that's just A, but this is molar absorptivity. And remember, what's the difference between A and the epsilon, the molar absorptivity? The difference is units. So if we're asked for molar absorptivity, the concentration must be in moles per liter. Now notice what they give you. They gave you milligrams per liter. That is not moles. So you've got to get that changed into moles, which you do through the molecular weight. You have to change the milligram to grams. So this is actually the concentration in molarity, and then just straight rearrange Beer's law. So the absorbance divided by the path length divided by the concentration. So this is what you should have for B. And again, almost everyone did this correctly. Few had problems with that. Okay, C said, okay, what if we make the cell 2 centimeters? So before, notice the first part, it was 1 centimeter, and now we're changing it to 2. So if we multiply B by 2, then the absorbance has to be twice as big. So this is your absorbance, and then they ask for T, so you have to change A to T, and you should have 0.122. And then D was calculate the absorptivity at 500 if the concentration is milligrams per milliliter. Now, this is actually the easier question compared to B, because that's the units they gave you. So it's just absorbance divided by B, divided by the C with milligrams per liter. And so you get this number. Do notice the units for both absorptivities. You have to have units. This one's m to the -1, centimeters to the -1. This one, liters per milligram centimeter. Okay, so that was number 9. 10, this is that case where, like the one we did in class, where I have 2 different solutions. So the first solution, you know, they tell us, can't see over the bar. This one, they give you absorbance. So they tell us A, they tell us B, they tell us C. This one, different path length, and they tell us T and they tell us B. So remember, the thing that links these, the thing that is the same for both of these is that molar absorptivity. So we can use this data to calculate molar absorptivity, and then use that to calculate the C here. Okay, so first one, rearranging the equations, the molar absorptivity is A divided by BC, so this is molar absorptivity. And remember, same solution, same wavelength, that number, absorptivity, molar absorptivity does not change. So now I just have to convert because they have given me transmittance. And remember, this is more than 1, this is percent T. So you have to divide it by 100 and then convert that to A. And then you calculate C, and that is your final answer there. Okay, and again, almost everyone did this correctly as well. All right, and then 11 was actually using a calibration curve. So remember, we talked about that for a calibration curve, you get the equation for the line, y equals mx plus b, and we're doing Beer's law. Okay, so here, y is A, and then x is C. So this slope, notice, is A times B, or molar absorptivity times B, depending which concentration you have. So if you have the equation for a line, then we can easily calculate absorptivity by taking the slope divided by the path length. All right, so looking at 11, they give us the calibration curve. And so as I just explained, absorptivity is simply that slope divided by B. And this is the molar absorptivity with the correct units. Then B said, okay, now I have an unknown, and they give you the absorbance, 1 centimeter cell. So what is C? Okay, so again, Beer's law, they gave us A, we know the molar absorptivity, same compound, same wavelength, that number's a constant. We know B, so I solve for C, and you should have 2.71 times 10 to the -3. And then C said, okay, now I have a sample. They give you C, and they give you a new B. And they want to know what is A, what is T. Now remember, absorptivity, same compound, same wavelength. So just doing the math, the absorbance is 0.172, and then transmittance, minus log of T, so we have to take 10 to the minus A, and you get 0.673. If you want to do percent T, then it's 67.3. Okay? Okay, so that is the homework. I will, after class, post the answers for all of the homework for chapter 1, 2, and 2 that you handed in. I will post that in the WeChat group and on Baidu and Dropbox and in Rain. So you can go back and study these as you review this for next week when we have a quiz. Okay, so that is the homework. All right, last time we started chapter 3, and we're going to finish that up pretty quickly here. It's a pretty short chapter. And remember, chapter 3 is about the components, the parts of an instrument. So last time we talked first about radiation sources, the light source. So what do you need to know about the light source? you should know there are two kinds of light sources, two big categories. They are continuum and line, okay? And then you should know, what are they used for? So continuum is used for molecules, and line, mostly atoms. Okay, that's what you need to know about radiation sources. Okay, so see, I'm helping you study for the quiz right now, making it really simple. All right, then we talked about the sample holder. And we talked about the light has to go through the sample holder, it has to be the right size. And what you need to know is what kind of materials do we use for the different wavelengths. So if I am in the UV, what should I use as my sample holder? Okay, quartz. All right, what about if I'm in the visible? I should use glass. And if I'm in the IR, KBR or NaCl. Okay, now what if I'm in UV vis together? Often we do the whole region together. Then what should I use? Okay, together, then you need to use quartz. Okay, because glass doesn't work in the UV. Okay, so that's what you need to know about sample holders. Okay, so today we're going to look at the other two components. We need to look at the wavelength selector and the detector. The detector will be very simple. And I mentioned this last time, the signal processor is always just a computer, so we won't talk about that anymore. But we do want to spend some time talking about this wavelength selector, because that's a very important part of the instrument. So usually when I want to do spectroscopy, I want to only look at one wavelength at a time. So for example, let's say I want to study 500 nanometers of light. Okay, that means I want to study 500. I don't want to study 510 or 550 or even 501. I want 500 and only 500. But the problem is when I try to select, I take all the wavelengths of light and I say, okay, I just want 500. I can never get just 500. What I actually get is a band of wavelengths. So this one in the middle, that's called the nominal. This is the one I'm trying to select. Okay, in my example, I'm trying to get 500. But I'm going to get some wavelengths that are a little bit higher and some that are a little lower. So there's an important term we use to talk about how many wavelengths do I get. And this is called the effective bandwidth. So what you do is you go up to the half height of the peak, and then we measure this distance here, and that's your effective bandwidth. So if I had an effective bandwidth of 50, what that means in my example is this would go up to 525, and this would be 475. So I'm trying to look at 500, but I'm actually getting 50 nanometers together, all together. So that's going to be a problem. So we need to talk about, okay, how can I select this wavelength? And someone's asking about the quiz. Again, the quiz is next week. You guys really need to pay attention to the details a little bit better. So I said last week the quiz would be in 2 weeks. The quiz is next week. Okay, so going on with the wavelength selector. There are 3 ways to select that wavelength, trying to get that 500 light. Okay, the first is to use filters. We're going to just block off the light we don't want. The second is to disperse. So disperse means to spread out the light and then select what I want. This will use something called a monochromator. And the third way is to use FT. And this is actually a math function that looks at everything at the same time. Okay, so let's look at the first type, the filters. These are the simplest and the easiest to use. They're just simply, well, there's two kinds of filters. So the first kind is what we call absorption filters. So these are just materials that are colored. And you know, if you've seen enough life, if we took white light, we shined it through a colored filter, some of that light would be blocked off. So that's an absorption filter. The second kind is what we call an interference filter. Okay, so let's look at the absorption filter. So these are just simply glass or gelatin with a dye that absorbs some of the wavelengths of light. Now, the bandwidths for these are very wide, 50 to 300 nanometers. Okay, so in my example, I'm trying to get 500. You know, if I'm getting 300, that means I'm getting 150 nanometers above it and 150 below. So very big bandwidths for these absorption filters. You can get filters with smaller bandwidths, but then the %T is very low, so they don't give you much light. Often what they'll do for these absorption filters is they use 2 or 3 together to help get smaller bandwidths. Because again, if I want to study 500, I want to study 500. I don't want all those other wavelengths. One of the positives of these is they are very inexpensive. So let me show you some different types. So the first one is what we call a cutoff filter. So notice it has %T of 1. That means all of the light goes through until you get to a certain wavelength. This one's about 650. And at 650 now, none of the light gets through. So that's called a cut-off filter. There are others that they call cut on, and they're a similar idea, except they would start at 0, and then at a certain wavelength, suddenly they let everything through. So that's one kind of filter. They just cut off or on at a certain wavelength. Now I said sometimes we can combine these filters. So notice here they've taken an orange cutoff filter, and then they've taken a green filter, and so that the light we get would be this. Now, notice that's still a pretty large bandwidth, and the intensity is quite low, you know, compared to the 100 we should have. We've lost half our light with this filter. Sometimes you can combine the cut on and cut off to get pretty narrow bands. So notice here they have used 3 different filters, and they've got us a pretty nice narrow band here and here. So one about 500 and one about 600, and pretty good intensity. Okay, so those are the absorption filters. So kind of the summary of the absorption filters. These are stable, they're easy to use, they're cheap. They're good in small portable spectrometers. This means a spectrometer that you want to pick up and carry around to different places. But the disadvantages, the very big bandwidths. That's a big problem. And again, I want to study 500. I don't want to study everything around it. The other disadvantage is you need a different filter for a different wavelength. So if I want to study 600, I need a different filter than to study 500. And I need a different one for 400. So every time you change wavelengths, you have to change filters. Okay, so that's the first kind of filter. So I told you there are 2 kinds of filter, absorption. The second one is called interference filter. And these work a little bit different. You have this material that the light comes in. And this light initially is all colors, all wavelengths. So the light gets in here and it bounces around back and forth, and some of the beams will interfere with each other. So in the end, you only get one wavelength of light out. So they all come in and one comes out. Now, of course, it's not really one. it's never one wavelength. It's a band. So what kind of band are we talking about? Okay, so the white light comes in, we get a narrow band out. And here are 3 different filters. And notice these bandwidths, 45 angstroms, that's 4.5 nanometers. And this one's 4.5. Notice this one, very small bandwidth, 1.5 nanometers, but the intensity is quite low. Okay, so notice these bandwidths are much narrower, but you still need a different filter for a different wavelength. Okay, so these interference filters, you can get ones that work in the UV, in the visible, all the way out to the IR. And they have much smaller bandwidths than the absorption filter. So remember, we said the absorption bandwidth was what? 50 to 300, very big. These, notice 1 to 10 nanometers, so much narrower regions of light. The interference filters also give you more light through than the absorption filters. Okay, all right, so that's the filters. And again, note, for the filters, if you change the wavelength, you have to get a different filter. Every time you change the wavelength you want to look at, you need a different filter. So kind of the summary for the 2 types of filters: absorption filters, big bandwidths, low intensities. The interference filters, smaller bandwidths, higher intensities. Okay, so this slide kind of shows you the most important points for these 2 kinds of filters. Okay, so that was the first way we can select wavelengths. Okay, the second way is to disperse the radiation and select that desired wavelength. And this is going to use something called a monochromator. Okay, now this word mono means one, and chromo means color. So what a monochromator does is it's going to take in all the light, and we're going to select one wavelength. Now, again, it's not really one wavelength. It's a band. It's always a band, but it'll be a much smaller band. Okay, so the monochromator is going to take the polychromatic light, the light of all the wavelengths, and we're going to get one wavelength or a small band of wavelengths. And the way it does this is to use a dispersion element. And there's 2 kinds. There's a prism and a grating. The prisms were the early one. Today, everything is gratings. But both of these can spread out wavelengths of light. And then you select what you want. Now, notice the bandwidths. Much smaller, 0.3 to 4. So remember, we had the absorption. That was 50 to 300. And then we had interference, that was 1 to 10. Notice the monochromator can go down to 0.3. So now I'm really getting that band much narrower when I want to look at these wavelengths of light. And the other thing about a monochromator is you can select any wavelength you want. Remember the filter, I said, oh, I want 500, I need this filter. I want 600, I need this filter. But the monochromator can select any wavelength you want. Okay, so let's look how they look. So we said first we need something to spread out the wavelengths. So you can use a prism, or these things here that kind of look like mirrors are what we call gratings. And you can kind of see that the light comes off of them. It's being separated into its different colors. So the prism works on refraction. So the white light comes in and then it gets bent in the prism, and shorter wavelengths are bent, are refracted more. So what happens is you wind up, all the blue light gets together, all the red lights, and then, if I want to study blue light, then I get the blue light out. If I want to study the red light, I would move this slit and get the red light out. So I get this small band of light. Now, as I said, the first monochromators were prism, But today, almost all monochromators use a grating. So in this case, again, you have the white light polychromatic coming in, and you have a mirror that fills up the grating. And then the grating will spread out the light in the different wavelengths, and then again, we select the wavelength that we want. So what is a grating? You may have studied these in physics, you may not. If you haven't, that's okay. We're not actually going to get into the theory of how they work deeply. There's actually all kinds of calculations you can do. We're not going to do those. We just want a very general understanding. So all a grating is it's a piece of quartz or glass or a mirror that has a bunch of small slits cut into it, very, very fine slits. If you're going to use the grating in the UV, you want about 500 to 1,000 of these slits per millimeter. Now, how big's a millimeter? You know, it's small. And I've got thousands of these lines in that millimeter. So these are very close together. Notice in infrared, they're a little bit less slits. Okay, now these gratings work on two principles, refraction and interference. Now, if I ask you, oh, have you ever seen a grating? Many of you might say, oh, no, never seen one. Maybe you've seen one in physics class, but actually, you all have seen something like a grating. You recognize what this is? Okay, this is actually a DVD. And you know, if you have a DVD or a CD, you know, you can actually get the light to hit it and you can see the colors coming out of the light. You actually see the separation of light. These are like gratings. These have a bunch of fine slits in them. And so when the light hits it, you know, if you get one of these and just play with it, you'll see the light. You see the colors come off it. This is what a grating does. There's diffraction and interference, and different colors come off at different angles. So the way the grating works, we take the white light, fill it up with the grating, and each color comes off at a different angle. Okay, so notice we get all the blue light together, all the green, all the yellow, all the red. And then out here, we can select which wavelength we want. Okay, so this will just show you this in a little movie. Not very exciting movie, but. So in comes the white light. We're going to fill up the grating. That white light contains all the colors. Okay, each color comes off at a different angle. And then we collect the different wavelengths. So, you know, here they're getting the blue light out. And then I say, oh, I want to study the green light. So then what they're going to do is just move the grating a little bit, or you can move the slit. And now we get a different color of light. Okay, so in that way we can study each color of light. Okay, so we looked at two kinds of filters, absorption and interference. And then we looked at the monochromator that spreads out the light and then selects it. Now, the way we would use this in an instrument, if you've got a tradition, there's different kinds of detectors. So the most common way to do this is say, okay, I want to look at the absorption of something at all of these different wavelengths. And remember, what I get from my instrument is this plot of intensity versus wavelength. So what I would do is I'd set the monochromator at my low wavelength, say 200 nanometers, and I measure intensity. And then I move it to 201, and I measure intensity, and then 202 and 203. So you do this, and you know, slowly you move it through each wavelength, and then you get this spectrum. And this takes a couple of minutes to do, to go, you know, from maybe 200 up to 750 nanometers. So that's the traditional way we would use this monochromator, and you can look at every wavelength, you know, one by one. There is a newer kind of way to detect this, and there are some detectors that can actually get this whole spectrum. Just look, you spread it out, and the detector looks at it all immediately. So you get this same spectrum, and this one, this way, the second way down here, only takes a couple of seconds to do that. Okay, so both of these will give you the same answer. This one takes several minutes because we look at one wavelength at a time. This one takes a few seconds. And next time in chapter 4, next chapter, we'll look at these different kinds of detectors and how they work. Okay. I did mention there was a third way to select wavelengths. That's to use something called Fourier transform, which is a math function. And this is very different. This does not select the wavelength. It actually looks at everything at the same time. So you do not use dispersion. You don't spread it out. You just measure everything simultaneously at the same time, and then you use a math function. So in time, you get something that looks like this, and then you have to have a computer. This is very complicated, but this can convert this to your spectrum, to frequency. And this is very commonly used in the IR. You maybe heard of FTIR. We will not talk about IR in this class, and FT does not work for UV-Vis, for UV-Vis. So we're not going to talk about this again. I just mentioned it, but this will not be important for our class. Okay. So we have talked about the radiation sources, 2 kinds. We've talked about the sample holder. We've talked about wavelength selector for each of these: absorption filter, interference filter, and monochromator. You should know the bandwidths. Now we have the detector. So the detector's job is to actually measure the intensity of the light. It's going to take the light and convert it to something I can measure easily, electrical signals, electrons. So there's 2 kinds. There's detectors that take photons and turn them into electrons, electrical energy. And then there's ones that use heat. And again, we're not looking at IR in this class, so we won't talk about these. And notice these detectors have several names. And when we get into chapter 4, we'll learn more about these names. So right now, you don't need to know the detector's names. You just need to know the detector's job is to convert photons to electrical energy that I can measure. Okay, so that's the detectors. So there'll be more on the detectors again later when we get into chapter 3. Into chapter 4. Okay, so that finishes chapter 3. Are there questions on chapter 3? Okay, so now we'll talk about the thing you all really want to know about, and that's the quiz. So the first quiz will be next week, so next Friday, and that quiz will be at the beginning of class, and we'll cover chapters 1 to 3. And I'm going to tell you more about the quiz in just a minute, but I'm going to actually go back and talk about something I talked about the first day. Quite honestly, I'm a little bit unhappy with this class. When I had to send out that message this week, and half of the students are missing assignments. And I realize that most of you that I am talking to now are not those students. But I'm not happy about it. This is unacceptable for people not to be turning in assignments, for things to be late. It's going to cause problems. And I am not going to continue to chase after you. So I am going to explain my policies one more time. And then if you continue to ignore them, That's fine, but you will not be happy with your final grade in my class. And I will state again, I do fail students if they do not do the work, okay? So those of you who are not being serious, you need to change immediately. So again, I will remind you that in this class, 40% of your grade are these quizzes, your homework, and your attendance. Now, most of the time, I'm not taking attendance. Today, I'm not taking it, but last week I did. So for attendance, my expectation is if you are in China, I expect you to be here in this class live, and I expect you to be here on time. That means 8:30 a.m. If you are not in China and you need to watch the video within a couple of days, our class time is Friday morning, no matter where you are at. And if you're waiting a week to watch the video, that is too late. If you are waiting a week to watch this video, you're finding out I have a quiz tomorrow and I haven't studied. That is not acceptable. Okay, for homework, that's due at the beginning of class. Now, most of you got this homework in on time. And I'll remind you, if you seriously attempt it, you turn it in on time, you get all the points. But if you aren't serious, it's incomplete, it's late, you will lose points. Now, these homework points are free points if you do it. So, it will help this 40%. But if you don't, then it's going to hurt your grade. If your homework is copied, I've found copied homework, you get zeros, both papers. And if it's more than 2 weeks late, I'm not taking it. Okay, now I'm sorry to have to come across so strong, but really I'm very frustrated with many students in this class, and this needs to change now. All right, let's talk about the quiz. So the quiz will be next week on Friday, as I said, and the quiz will last 35 minutes. So it will be timed, just like that practice quiz. So once you open it, you cannot get out, you cannot stop it. You have 35 minutes to finish it. And it will cover chapters 1, chapters 2, and chapters 3. We will take the quiz on rain. Now, because some of you are outside of China and it's the middle of the night, 2:30, 3:30 a.m., for those outside of China, I'm going to let you take the quiz a little bit later. So you can take the quiz between 12:50 and 2 p.m. China time. So Friday afternoon. Now, originally I said 2 p.m., but I found out that the environmental students have a class starting at 1:30. So they can take the quiz starting at 12:50 p.m. up to 2, but you must start it by 2 p.m. Now, to do this, your name has to be on this list. Okay, if your name is not on this list, you cannot take the quiz in the afternoon. Okay, everyone else takes the quiz at 8:30 a.m. China time. Okay. Now, if you think your name should be on this list, you need to contact me and explain why it should be. Okay. If your name is on this list, there is a new RAIN class that you need to join to take the quiz. Several of you have tried to join this class, and I have taken you out because your name is not on this list. Okay. All right, so if your name is here and you do not join this class, then you have to take the quiz at 8:30. Okay, so if you are in China, your quiz time is 8:30 a.m. next Friday morning. If your student number is here, then you can start the quiz between 12:50 and 2 o'clock next Friday, China time. Now, notice the quiz starts at exactly 8:30. or if you're the second time by 2 p.m. And it's timed. So if you come to class late, you come to class 5 minutes late, 10 minutes late, then your quiz time gets shortened. Okay? The quiz ends at 9:05. So if you are late, you get less time for the quiz. Now, I know you don't like 8:30 a.m. I know many of you have trouble with that time, but sorry, that is when it is. And so I'm not going to put up with being late. Quiz starts at 8:30. All right, so the kinds of questions. There will be 5 multiple choice questions, and we choose one answer. There is one question that has 2 answers, and it tells you very clearly, choose 2 answers. So there'll be 5 multiple choice. There are 5 choose one questions where I just give you 2 choices. You know, is it this one or this one? Just 2 choices. There are 6 points of short answer. So these, you don't have to write a sentence. You just need to give the answer, and you can just type them into the box to give me those answers. And then there are 9 points that are calculations. These you have to do like your homework, where you write them on a paper and then take a picture. The instructions for the calculations will say this. So submit your answer by picture. If I tell you to do this by picture, you must do it by picture, okay? So you have to write it by hand. You must have your name and student number. You must show me your work, your equations, and the numbers used. Clearly indicate your final answer. That's the box. You need to pay attention to units. You need to pay attention to significant figures. Okay, just like the homework, all of those things are important. Okay, so those are the kinds of questions that are on the quiz. All right, now, because we're remote, you guys are fortunate. The quiz will be open note, open book. You can use whatever materials you have there, the PowerPoints, the book. You really should not be consulting other people or the internet. That's cheating. So you need to do your own work. You do need to study like it's closed book. And the reason is you actually do not have time. If you just think, oh, I'll just take the quiz and I'll find all the answers in the book, you do not have time. So you need to study like it's closed book. And then you'll have time to look up a few things maybe you're not clear on. But if you plan to look up everything, you will run out of time. Okay? And you also, during the quiz, you need to pay attention to the time. You know, you can't wait at the last minute and say, oh, I have 1 minute and I have to take my pictures and put them in. And then you come to me and you say, teacher, I ran out of time. No, that's your problem. You need to pay attention to the time. You need to know at 35 minutes, that quiz closes. It's over. So you have to watch the time during the quiz. Okay, now what should you study? Well, you should study all of the homework problems and keywords in the book. So at the end of each chapter, there's a list of keywords. You need to look at those words. You need to know, why are they there? Why is this word important? What does it mean? You need to look at all of the homework problems in the book. Now, I have asked you to give a few, to me, calculations, but there are many other questions that you need to look at. Now, you have the answers to all of those, but you need to make sure you understand all of those homework problems. Make sure for the quiz you have a calculator, paper, so you can write your problems, something to write with that are there ready to use. You can use your phone, of course, as a calculator, but it's probably slower and you'll be using your phone for other things during the quiz, so it's better to have a calculator. So make sure you prepare that in advance. I will not give you any equations or constants, like H or C. All of these equations you've used in your homework, you need to know yourself. And since it's open book, you shouldn't have trouble finding them. Okay, one other note that some of you may not know, you can actually use RAIN on your computer. So if you go to this website, you can simply use your WeChat and scan into your account with this code. And this is actually a faster way, because you can use your whole computer screen and you can see everything. And so you can answer the multiple choice and the short answer you can type on your keyboard. So some of you might find this to be an easier way to do these questions than your phone. Now, you still need your phone to submit the pictures. You can't really submit a picture by the computer. So you are going to have to use your phone for sure. So you should actually, if you want to use your computer, you should sign in with both. Okay, and you can do that. You can be in on your phone and on the computer both at the same time. It's not a problem. Okay, so I recommend that 5 minutes before class, you should be signed in and ready to go. So as soon as the quiz is released, you can start it. Okay, because again, if you are late, you're going to miss quiz time, and that will hurt you. All right, finally, if you have questions, you can always ask them in the WeChat group. Again, I will state, I will not accept personal friend requests. You have to ask me in the group. You can send me an email, and you can also chat with me in RAIN if you can figure out how to do that. No one's done that, but you can do that. Okay, so that's the information about the quiz. Note that we do have class after the quiz. The quiz will be the first half of class, and then we will have a shorter class on Zoom at 9:15. So you don't get out of class. We don't have time to waste a whole half class after that. Okay, all right, so that's the information about the quiz. After class today, I will post the information, the homework answers that you turned in, and I will also post these slides that I've just shown you about the quiz. Okay, are there any questions? Okay, then we will go ahead and take a break here. So we'll take a 5-minute break, and then we're going to start chapter 4. And actually, the first part of chapter 4 is kind of, some of it's review, so it can help you. All right, so I'll see you in 5 minutes. Okay, so let's move on now to chapter 4. So first we want to look at some ways that we classify or divide up spectroscopy experiments. So sometimes when we talk about the experiments, we talk about them as either absorption or emission. Sometimes we talk about spectroscopy as being for molecules or for atoms. And then sometimes we talk about it in terms of what kind of wavelength of light are we interacting with, or what's the type of transition. Now, in our book, we have 2 more chapters on spectroscopy. So this is chapter 4 and 5. So to just kind of show you where these fit, chapter 4 and 5 both deal with the absorption of light. Chapter 4 deals with molecules absorbing light. Chapter 5 is atoms absorbing light. And both of these will be talking about absorbing UV vis light. Now, there are lots of other methods for spectroscopy that we will not talk about in this class. There are methods that talk about emission of light. And there are methods that talk about emission for molecules and emission for atoms in the UV vis. Those are very important methods. They are very useful methods, but we don't have time in this class. There's methods that talk about absorption by molecules of IR light. That's an extremely important method, but again, not for this class. And there's a method that talks about absorption by molecules by the nucleus that absorb RF. And again, a very important method called NMR, but we won't talk about that in this class. And those are just basic methods. There are many other types. Okay, but again, our focus will be the absorption of UV vis by molecules in this chapter, and then the absorption of UV vis by atoms in chapter 5. Okay, so when we get into these instruments, we're going to start looking at 4 and 5, specific techniques. Something you should look for whenever we talk about this, a method, there's always kind of be 3 parts. We'll talk about the instrument, what's inside. We'll talk about the theory, how the measurement works, and then we'll talk about the application and use. So you'll see these 3 parts as we go through chapter 4. If you've looked at the PowerPoint slides, you know there's a lot of them. This is probably our longest chapter that we have in the book. Okay, so we're going to start out kind of with an introduction. So the name of the chapter, Ultraviolet and Visible Molecular Absorption Spectroscopy. So this tells you what I've already told you, the kind of light we're going to talk about, UV vis. We're talking about molecules, and we're talking about absorption. So let's go ahead and define, when I say UV vis, what wavelengths am I talking about? So the visible region is from 400 to 750 nanometers. That's the light we can see with our eyes. Often Chinese books will have up to 800 nanometers. So some people extend it a little bit further. Both are okay. Okay, then the UV, that's from 200 to 400 nanometers. So that's the light that's just below visible in the wavelength, a little bit higher energy. And then there's actually another region called the vacuum UV. This is from 200 nanometers to 10 angstroms. This is 10 nanometers. And this is where air and water will start to absorb the light. And so you need a vacuum to do it. So that takes some special instruments. And so we will not really consider this light because it takes extra components for your instrument. So our focus again will be the visible UV light. Now I've talked about the type of light determines what kind of transition we have. Okay? And you should know there are 3 kinds of transitions for molecules. Okay, what are they? They are vibration, rotation, and electronic. Okay, you should know those 3 kinds of transitions. So when we work with UV light, this is the light that has the right energy to excite electronic transitions. So in this chapter and in chapter 5, we will be talking about electronic transitions. Okay, so at the measurements, what do we use it for? And we'll get more detail later, but just overall, this method is very useful to do quantitative determination of both inorganic and organic compounds. Okay, so quantitative determination, what does that mean? How much is there? And what do we use to tell us quantitative information? Well, that's Beer's law. Okay, and notice that Beer's law tells me absorbance is proportional to concentration. So my quantitative information comes from the absorbance, because I know that that is related to concentration. Those 2 are linked. We can also, with this method, do a little bit of qualitative identification. So what does qualitative mean? What is it? Primarily for molecules, what this will tell me is it'll give me a little bit of structural information. It doesn't actually give me a lot of structural information, but it will give me a little bit. And this structural information will come from the wavelengths. Okay, so the absorbance gives me the how much. The wavelengths give me the what is it. Beer's law also works for a mixture of species. If you have more than one species together and they all absorb, Beer's law is additive. We will not use it to do that, but just a good thing to know that it does work for mixtures. Okay, so now we need to go back and take a closer look at Beer's law and the measurement. So remember, for an absorption measurement, I'm measuring here what last time we called P0. This one uses PI, but it's the same thing, and P, and they're using PE in this picture. So remember, we measure the intensity or the power of the incoming light, and then we measure the intensity or power of the light after absorption. And last time we said that's how we measure absorbance and transmittance. Okay, but now there's a problem we need to talk about. If I take my cell, okay, this cuvette, and I fill it up with just water, nothing else, I will actually lose 8.5% of my light. Okay, some of the light will bounce back, some of it could be scattered, but what that means is if I take a measurement of water, I'm going to get an absorbance of just water. And remember, the water should have no analyte. So that's a problem. So we have to actually compensate. We have to deal with that problem. So the way we do that is we're going to compare the light that goes through the sample to the light that goes through a cell that's filled only with the solvent. Okay, now notice, only the solvent, that is my blank, also called a reference. So from now on, when I talk about measuring transmittance or absorbance, what we're really measuring is P of the solution divided by P of the solvent. So this solvent, that's your blank, your reference. This P solution, that's your sample. Now, we're still going to just talk about P and P0, but you have to know that we have to actually do this as solution compared to solvent. It's always going to be compared to the blank. So from now on, P0 is the blank. And that cell with just water in it. Okay, and here's that same thing with absorption. Okay, so that's the first thing we have to think about. Now, in your homework, you had to do lots of calculations with Beer's law, but most of those calculations are not how we would use it in real life. Okay, in real life, we would make a calibration curve. Okay, and we can get the equation of the line. It'd be like that number 11, that last problem. So we need to take a closer look at what are the limitations to Beer's law. You know, when is Beer's law applicable? Or what's the applicability? Now, what does that mean? Well, that means when does Beer's law work? Okay. Beer's law actually does not always work, so we need to know the conditions for where Beer's law works. So the first one is there can be no interactions between molecules, because if molecules start interacting with each other, it changes how they absorb. Okay, so this means we're going to need dilute solutions. Usually your concentrations have to be less than 0.01 molar. Okay, second thing you need for Beer's law to work is the light beam that we're shining through has to be one wavelength, monochromatic. Now, if you think about what I just talked about in chapter 3, do we ever have one wavelength? Nope. Remember, we talked about we always get a band. So this could be a problem. We're going to have to look at that very closely. Okay, third thing you need for Beer's law to be true is the analyte can't be doing any other kinds of chemistry. It can't be reacting with itself. It can't be breaking apart. It can't be interacting or reacting with the solvent. So if anything's happening to my analyte to change its form, then you're changing how it absorbs. These all absorb differently than A. So we can't have any of that stuff going on. Okay, so as we continue to look at these limitations to Beer's law, if we look at the equation, we say, okay, the absorbance should be proportional to C. It's also proportional to path length, E. And almost always, absorbance is directly proportional to path length. Now, if you make the path length twice as big, absorbance is twice as big. If you make the path length 3 times bigger, absorbance is 3 times bigger. Okay, but often absorbance doesn't always exactly go up or down with concentration. It's not exactly proportional. So we have these 3 kinds of limitations or deviations. These are places where Beer's law doesn't always follow the rule. You know, the rule says absorbance should equal absorptivity times path length times concentration. But this is not always true. So we need to look at what are these deviations or limitations. Okay, so the first one, the real limitations to Beer's law. This is the case where the molecular interactions are happening at high concentrations. And what happens is the distance between molecules gets smaller, so the molecules start interacting with each other. Sometimes you get hydrogen bonding between the molecules, and that changes how they absorb. It changes that absorptivity. So these are the cases where that calibration curve at high concentration is no longer linear. You know, we cannot do measurements out here. You know, now we're stuck with these low concentrations. So if the absorption is nonlinear, you know, we can't use that. We have to stay in the linear portion, which again means concentrations less than 0.01 for most species. If you have a lot of salt electrolyte, a lot of ions in your solution, you will get some of these same effects. So you also cannot have a high electrolyte concentration. So again, normally, as long as the concentration is less than 0.01, we're okay. There are some molecules that have to be even lower because they really like to interact with each other. Okay, so that's what we call a real limitation to Beer's law. Next is these things called chemical deviations. So this is where the analyte is doing some chemistry in the solution. Common example, a weak acid. So if I have this weak acid, it will dissociate and form this conjugate base. Now, most of these are organic compounds, and so this acid form has one color and the base form has a different color. But often their absorption spectrum actually overlap. So you can see that both of these compounds, they absorb at 430 and at 570. But notice their absorptivities are different. Okay? So at 430, notice that the base, In minus, absorbs stronger, but at 570, the acid form absorbs stronger. Now, in a solution, you're going to have both of these. We cannot stop this equilibrium. You're always going to have some of the acid and some of the base. And what happens is if you try to measure absorbance at 430, you're going to get this curved line. If you measure at 570, you'll get a different curved line because both of these species are absorbing. Now, it is possible to do calculations to figure out what's coming from the acid and what's coming from the base. I think there's an example in your book. We will not do that calculation. It's a little bit complicated. It's not too bad, but we won't do it. But you should just know if there's other chemistry going in, then your calibration curve will not be linear. Okay, so that's a chemical deviation. And then finally, we need to look at the instrumental deviation. This is where the problem has to do with how we're making the measurement. There's actually a problem with the instrument. So I mentioned that in Beer's law, the light has to be monochromatic. And even if we have a monochromator, you always get a range. Remember, I said the bandwidth is 0.3 to 4 nanometers. Now, it's a small range, but it's still a range. I'm not getting one wavelength of light. Now, why is that a problem? Well, remember my example. I'm trying to look at 500 nanometers. And let's say that I have a bandwidth of 4. So that means I'm getting light from 498 to 502. Okay, now, if the molar absorptivity is close to the same at all of these numbers, okay, remember A equals absorptivity B C. So if this number is about the same for all of these wavelengths of light that I'm getting, then I'll still get a nice calibration curve. It's not a big problem. But if the absorptivities are very different, you can see like here, one has an absorptivity very high and one is low, now it's going to deviate badly from that line. This is a significant error. So how can we fix this error? Well, the way we fix this is that we always try to take our measurement up here at the top of the band. Because up here, the absorptivity here and the absorptivity here are very close to the same number. So you're going to get a nice linear calibration. But if I take my measurement here, this absorptivity and this absorptivity, they're quite different. So now you're going to get a curve instead of a line. So you're going to have a big error. Okay, so this is one reason that we always make our measurement up here at the top of the band. It's so that it will follow Beer's law. Now, there's actually a second reason why we always measure up here at the top of the band and not over here on the side. What do you think the second reason is? Any ideas? Why would we always want to measure my absorbance up here at the top? Okay, well, notice up here at the top is where the absorbance is the biggest. So up here at the top, this is where my signal is the biggest. Okay, so there are two reasons we always measure at the peak of a band. Okay, and by the way, this maximum is called lambda max. Okay. So two reasons. First, so that we follow Beer's law. Second, at the biggest signal, maximize the signal. Okay, so usually as long as the bandwidth of the monochromator is 1/10 the bandwidth of the peak, this will work fine. So as long as this peak is from 3 to 40 nanometers wide, then this problem with the non-monochromatic light is not a problem. And most peaks are this broad. So usually working at the top of the peak prevents this problem. Okay, there is one other kind of instrumental deviation we need to look at, and that's something called stray light. So remember, my monochromator, its job is to select one wavelength of light. You know, in my example, I want the 500 nanometer light. So the monochromator is going to select that small band around 500, and then I'm going to measure the absorbance of my sample of that small band of light. But in that monochromator, there's mirrors and there's blends and there's light bouncing around. So sometimes other wavelengths of light also get out. You know, here we said, okay, I'm measuring 500, but Now, let's say this stray light, this is extra light that comes out. It's a different wavelength. It doesn't matter what wavelength, but it's not 500. So what happens is this light goes through my sample, and the sample, we're measuring this 500, but some of this light is not going to be absorbed by my sample. And that light is then that extra light, it's called stray light, is going to get to the detector. So now this detector is still seeing the 500 light that's not absorbed by my sample. So some of that, some of that gets to the detector, but now we've also got this extra light, this stray light. So that makes the detector see too much light. So that means the transmission is going to be too high, or the absorbance is going to be too low. And if you have a very high concentration of sample, okay, that means your sample absorbs most of the light, so the amount of stray light becomes big compared to the light you're trying to measure, so that you get a larger error. So this just shows you an example of different amounts of stray light. So if there's no stray light, we get our nice linear calibration curve. But as we get more stray light, notice the curve gets worse and worse and worse. Okay, so that's instrument deviation from stray light. Okay, so that's a little bit more about Beer's law and some of the things we have to look out for as we use it. We now want to turn to the instrument and look at what's inside these spectrometers that can measure absorbance. And there are many, many different kinds you can buy. Some of them are quite cheap. Some of them are very expensive, but they all have the same basic parts. And you should know, what are these basic parts? Well, there's a light source. There's a wavelength selector, there's a sample holder, there's a detector, and then the signal processor, the computer. So notice in this one, they've got a light source here. From 2 all the way to 7, that's actually the wavelength selector. Here is my sample holder, and then here's my detector. So we now want to look, we've spent some time looking at these generally, but we now want to look at more detail at the source and the detector that we didn't in chapter 3, we just said very briefly. So we're going to get into some more details. All right, so sources. So remember, from chapter 3, there are 2 kinds of sources. They are continuum and line. Okay, and remember, for continuum, we said we use those for molecules. Line, we use for atoms. Okay, so this is molecular spectroscopy, so we are going to be looking at continuum sources. And so we're going to actually look at 3 that are commonly used in the UV vis region. So the first one is what's called a tungsten lamp. So this is actually just a piece of tungsten that is heated to a hot temperature. And so when you heat something to a high temperature, it will give off light. Okay, so you get this emission of light. So this is actually the most common source that we use for visible light and also some IR. It will give us wavelengths of light between 350 all the way up to 2500. Now remember, for our uses, we only need up to 800 if you're using the Chinese system, or 750. Okay, so this is going to give me visible light. It has a glass bulb that's around this tungsten filament that's in a vacuum. One important point is you do have to control the power to it, because notice that if you change the voltage, it has a huge effect on the wavelengths, the energy of light that you get out. So you have to control the voltage very closely. So this is a picture of what it looks like. It's just got this tungsten filament in here. We heat it up really hot, and out comes light. And you can see these are the wavelengths of light we get. So the first lamps were actually just these tungsten wires. they have actually improved them now so that modern instruments use what's called a tungsten halogen lamp. So this is the same thing. You still have this tungsten wire, but now we're going to add some I2 in here. And what happens when that wire gets hot? Some of that tungsten goes into the gas phase. And then that gaseous tungsten will then combine with the I2 in the gas phase, and it makes this tungsten iodide compound. And then this then redeposits right here on the filament. Okay, so that what happens is it makes the filament last longer. Okay, because you're taking some of the solid off and then you put it back on, so it lasts longer. This also actually moves the light that you get out down into the UV, so we can get down to about 200 nanometers. That does mean we have to change that bulb. Instead of glass, we have to change it to quartz so the UV can get out. So this is what the light looks like that we would get out of the tungsten halogen. Now notice the light down here in the UV, 200, it's still a very low intensity. It's much stronger at these higher wavelengths. Okay, so this is a very important source because this is the main source that we use for visible light today. Okay, now for UV, the source for that is something called a deuterium lamp. So deuterium is a form of hydrogen. So what they do is have a bulb with D2 in it, and we put current through it so that the D2 gets excited. Okay. Now once it's excited, so we have my ground state down here, and then I get this D2 up here in an excited state. Now what happens is there's actually a whole bunch of different energy levels here. And so when this D2 comes back down, it can come to any of these energy levels, okay? Because these guys are colliding and there's all these different kinetic energy levels. So you actually get a continuum of light. You get an emission spectrum that looks like this. So notice it gives me light from over here at 160 out to 400 nanometers. And this is what the deuterium lamp looks like. So this is my UV source. Okay, now most often you're going to be doing UV vis together. So what would you use for the source? Well, you actually use both of these. So you use deuterium for the UV because deuterium is a stronger source in the UV. And then when you get to this point where these two intensities cross, then you switch over to the tungsten lamp and use that for the visible. So if you're only doing UV, you would use the deuterium lamp. If you're only doing visible, you would use the tungsten, or actually tungsten halogen today. And if you're using both, then you need both sources, the deuterium and the tungsten halogen. Okay, one other source is something called a xenon arc lamp. This is xenon gas at a high pressure. They put a charge through it, and you get a very intense source. Notice this gives me everything. It gives me UV and visible. So you might think, oh, well, this is the best source. It gives you everything with one source. But the problem with this one is right here. This is a very strong source. Sometimes it's too strong for your samples. So this is actually used more for emission experiments. You can use it for absorption, but again, the most common are the deuterium and the tungsten halogen. Okay, so those are the sources. All right, next, sample holders. Now we've already talked about what we need to know here pretty much. We need something to hold my sample. It has to be transparent and it has to be the right size. So again, for the UV, these are the materials we're looking at. We've already talked about this in chapter 3. If I'm in the UV, I'm primarily going to use quartz or fused silica. They're similar. If I'm in the visible, I'm going to use glass, or there might be some plastics. There are other materials that you can use, but again, the most common, quartz and glass. Notice I added this spectrum that shows you, the quartz and the fused silica. Notice that they work all the way down to the UV and they work all the way up. Okay, glass doesn't work down here in the UV, so that's why we can't use it. Okay, so before I said, okay, if we're in the UV, we have to use quartz. If we're in the UV vis, we have to use quartz. What about if I'm just in the visible? And I told you, well, we use glass. Now, looking at this, does quartz work in the visible? Sure, it works just fine. So can we use quartz in the visible? Yes, we can, but notice one of these little cuvettes in quartz is about $80 US. The glass one, 35. So if you're going to break it, which one would you rather pay for? Well, of course, glass. So if we're in the visible, we usually use glass because it's cheaper. Now, notice plastic is really cheap. And so you can use plastic, but usually the plastic you use one time, then you throw it away. And then also you have to be careful. Some of the plastic will react with organic solvents. Okay, so sample containers, really nothing new. They do come in lots of different sizes and shapes. Notice some have very long path lengths. Some of them are actually designed to hold very small volumes. Some of them, your sample can actually flow through. It go here, comes in, and then comes back out, so you can measure a moving system. So lots of different sizes and shapes. But by far, the most common is the 1 centimeter cell. And this is a picture of what it most commonly looks like. Usually it has 2 sides that are frosted. That's where you put your fingers. And then the light shines through the clear side. But again, there are other shapes, other sizes, but this one is the most common. Okay, so that's the sample cells. Okay, so we have looked at the source. And we said, okay, the main sources are UV, deuterium lamp, visible, tungsten halogen. Okay, and then there is the xenon, but it's not super common for absorbance. We've looked at the sample holder. Okay, this wavelength selector, we've looked at that. That's just what we learned in chapter 3. Usually you're going to use a filter or a monochromator. If it's a higher quality instrument, you're going to use a monochromator because then we can select every wavelength and have the smaller bandwidth. So the wavelength selector, nothing new here. That's from chapter 3. Okay, which brings us to the detector. So the detector is the thing that's going to convert non-electrical information. Okay, and by non-electrical information, we mean light. It's going to convert light to electrical information. They usually electrons so that I can detect this light that's being absorbed. Okay, so for a perfect detector, there's several things that you want. You want it to be very sensitive, so that it can measure very low levels of light. You want a good signal to noise. You want it to have the same response for all wavelengths. You want it to respond very quickly. When the light hits, you get a response. And if there's no light, you want 0 signal. That response you get with no light is called the dark current. And most detectors have a dark current. They have a signal even with no light. So often we have to set those to 0. We have to make a circuit to adjust it to 0. Okay, so this is what we want for an ideal detector, along with a direct relationship between the amount of light and the power. Now, in fact, we never get all of these with a detector. We never get everything we want. And there are several different kinds of detectors. And notice, I said what we really want is a detector that's way up here, very sensitive, and gives me the same response at all wavelengths. And notice we don't have that. We have some that work very sensitive in this small wavelength region. You know, we have these that work everywhere but have low sensitivity. So as we look at the detectors for UV vis, there are 2, 3, 4, 5 that are most common. This top one from that table, this is a very old one and is not used. But these 5 are all commonly used as detectors. So starting next time, we will be looking at these 5 detectors, and we're not going to look at them in detail. I'm just going to kind of explain very, very simply how they work. And we're going to learn about, you know, are they sensitive? Are they expensive? Can they measure one wavelength or lots of wavelengths at the same time? Okay, but that will be for next time. Okay, so for next time, beginning of class, quiz. So you need to sign on to RAIN before class. Most of you, that's 8:30. And take the quiz. And then after the quiz at 9:15, the Zoom class, where we will start up right here in chapter 4. Okay, so that is it for today, unless there are some questions. There's still a few of you who maybe need to talk to me about quiz times or anything. You can do that. Again, email, WeChat, RAIN, now. But again, if I don't hear from you, then those 10 people can take the quiz in the afternoon. Everyone else, 8:30. Okay, any questions? Okay, you are free to go. I'm going to stick around for just a couple minutes to see if there's any questions.